quality of the regression model, R squared. So the main measure for the quality of a regression model is the R squared measure. And I have a reference here to the adjusted R squared, but notice it's just a small adjustment that is often done in the programs and the applications, but the main idea is the same. What the R squared is essentially difference between the residuals of the model. So if you remember the residuals, why always does that? I don't know why. The residuals of the model divided by the actual values of the model. And this S is variance. So it's a variance in residuals, divided by the variance in the actual dependent variable. Okay, so essentially it gives us some ratio of variance of the errors, the residuals, which is the difference between y and the predicted y by the model, right, by the line. Remember, the line is not the point, so there's a distance between the line and each point. So this variation gives us a number which we call the R squared, or adjusted R squared. The adjusted R squared actually controls for the number of variables you have in the model, so it's a slightly better measure. And essentially it gives us the percent variation. It's the percent variation in the values of the dependent variable that are explained by the whole model. So the higher the value of the R squared, the better, the more predictive or generalizable the model is. Essentially gives us a measure of error, as we saw, the variance of error, the distinction from the line of the model to the data points. It's also a way to see how much we can generalize the linear model to other events outside of the data. So if we build a regression model, let's just take a look at this here up top. We'll see all the different predictor variables that we included, and then we have the estimate. The estimate is also the coefficient, and each one has a p-value, and we also have the R squared, or the adjusted R squared number for the whole model. It's one number for the whole model, and this means that this whole model explains 25.4%. 25.8% of the variation of the dependent variable. Is this good or bad? It's neither good nor bad. It's not terrible. Sometimes some models can explain much less. It's not great, but it's not necessary that we need to explain everything. As long as we can explain some variation is good. I would say this is a reasonable model, but if you're over 0.1 or over 10%, and of course from that, the more the better. And here we have another model. Notice that this one has less variables, and it increased slightly, but it's almost like a rounding error. It went from 0.84 to 25.85, so very slight increase. I would say this is kind of almost negligible, but the textbook seems to think it's a big deal. So you can see that if you remove change variables, you can change the R squared value, and that's part of the goal here, is to think about how we can create better models that have better better R squared. So there are two model selection strategies, and let's just go right into it. So it's pretty straightforward. One is backward and one is forward. So backward elimination is to begin with all the potential predictor variables and remove variables one at a time. So it's kind of like what we saw here a little bit. So you have a bunch and we include all of them, and then we kind of started removing. And you may say, wait, why did we remove these? Well, note that these were like non-significant. So if they're non-significant, then maybe they're non-significant. There's no association between them and the dependent variable. So why keep them in the model? Get rid of them. So that's backward elimination. Begin with all of them and then remove one by one depending on the some of the results. And the other one is to begin with the fewest predicted possibles and include variables one at a time to improve the R-squared. So you may begin with some things that kind of make sense. You know, if you're trying to predict interest rates, so it makes sense to put the bankruptcy of the person and the credit checks and all these other variables. And I think it's a more sort of scientific, regular science kind of approach by focusing on the variables that we can actually explain, can have a causal effect on the dependent variable. So both approaches above are also possible on p-value for each variable. Anyway, so we can do the backward and the forward selection with the R-squared. Okay, so that is eliminate or add variables to improve the R-squared, but also note that we can take the same approach with the p-value. When we remove variables from the model, we may change the p-value of each of the remaining variables and also the coefficient. So let's see if it changed much here. And this one didn't change much. I see a small change difference here for bankruptcy. 3864, 0.3864, and then here's 0.369, but we can have other bigger changes. So we can do the same. We can also do the backward elimination on the forward selection with the p-values for the model as well. Once again, I think it's always good to think about the actual causations, especially when we're doing regular science and you want to explain things rather than just create a predictive model. So focus, you know, using the predictor variables that are actually can be explained to have a causal relationship with your outcome variable of interest. And we can do this backward elimination and forward selection with it based on the R-squared, changes in the R-squared, and also based on the p-value. So which one is better? Should we just focus on p-value or R-squared? I think both of them are useful, but once again, it's important to think of the variables that we can explain, that kind of makes sense to be there. Sometimes we can include variables that we have no idea why they're there, but they seem to have helped the model and also increase the p-value and also has a high p-value. So I would suggest that we include variables that make sense rather than just anything that increases the numbers. So that's my approach. Next, we're going to be talking about checking model conditions.